Hey guys, welcome to EDUKEM channel. In this video lecture, we'll talk about next part of solid state. The subtopic that we are going to discuss about crystal system. Next, we'll discuss about the 2D and 3D packing, that is two-dimensional and three-dimensional packing. Next, we'll discuss about some voids, or voids are nothing but your empty space. So there are two types of voids. One is tetrahedral void, another is the octahedral void. This picture shows about the arrangement of atoms in three-dimensional system. So without a doubt, let's start. Talking about the crystal system. So in the nature, there are total 7 crystal systems exist. Those crystal systems are cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. So here is a picture of a simple cubic crystal system. Now we have to remember the different side length. So this x, y, and z axis are, this is our x axis, this is our y axis, and this is our z axis. So in this axis, the edge length are A, B, and C. These are edge length, which are respective of x, y, and z. Okay. Now alpha, beta, gamma are the opposite angle representing this x, y, and z. How it is? You see, this is x-axis. That means the opposite of x-axis is the alpha angle. This is our y-axis. The opposite of y-axis is the beta angle, and this is our z-axis. The opposite of z-axis is the gamma angle. In the next slide, we will discuss detail about this 7 crystal system. Now, crystal system. So as we have discussed about 7 crystal system, we will go one by one. First is the cubic crystal system. So next is the Bravais lattice. What is Bravais lattice? Bravais lattice means in any crystal system, if you put atom. So there are total 14 Bravais lattice exist in the nature. Okay, we will go one by one. So first is the cubic, and Bravais lattice. Bravais is the name of the scientist. In this cubic lattice, the arrangement that is possible are first one is primitive, next face centered, and body centered. See what is the meaning. In this cubic system, if you'll put atoms at the corner, that will be the primitive Bravais lattice. Another possibility is if you'll put the atoms at the center. Okay. Another possibility is if you'll put the atoms at the face. So these are the possibilities. So how many possibilities for cubic? That is one is primitive, second is the face center, third is the body center. So 3 lattice are possible. Next, talk about the edge length. So ABC edge length and 3 AB, A is equal to B is equal to C. And all these alpha, beta, gammas are 90 degree. Examples are NaCl, zinc blende, and copper. Next is the orthorhombic. Orthorhombic, the Bravais lattice possibles are primitive, face centered, body centered, and end centered. You see, this is the orthorhombic, where A is not equal to B is not equal to C, and alpha, beta, gamma are 90 degree. You see, this alpha, beta, gammas are 90 degree. Alpha, beta, and gammas are 90, whereas A, B, C, they are not equal. Next, you will see the example: rhombic sulfur and potassium nitrate, BSO4. These are the examples of orthorhombic. Next one is the tetragonal. Tetragonal Bravais lattice possibles are primitive and body centered. You see, this picture is the tetragonal. In this crystal system, A is equal to B, but that is not equal to C. And alpha, beta, gamma are 90 degree. Next one is the monoclinic. Monoclinic Bravais lattice possibles are primitive and end centered. So this is the monoclinic picture. Here A is not equal to B, not equal to C. Alpha and gamma are 90, beta is not 90. Examples are monoclinic sulfur, Na2SO4, 10H2. So how many Bravais lattices are possible in this picture? So 1, 2, 3, again 4, 5, 6, 7, 8, 9, 10, 11. So you remember here it is 11. In the next picture, we will see the next part. Next one is trigonal or rhombohedral. Bravais lattice possible, that is primitive. A is equal to B is equal to C. Alpha, beta, gamma 3 are not equal to 90. Example is HGS. You can write any of the examples. Next one is triclinic. Bravais lattice possible, that is primitive. A is not equal to B, not equal to C. alpha is not equal to beta is not equal to gamma. That is, three angles are not 90. And examples are potassium dichromate, CuSO4.5H2O. Okay, this is the triclinic picture. And next is the hexagonal. Bravais lattice possibles, that is primitive. A is equal to B, but it is not equal to C. Alpha, beta is equal to 90, gamma is 120, remember. And examples are ZNO, CDS. So in the previous slide, we saw that total 11 Bravais lattices are there, but here it is adding 3. So 11 plus 3, that is 14. So you remember total 14 Bravais lattices are possible. Now let's just talk about the crystal packing. So packing of constituent particles. The structure of crystalline solid is determined the packing of the constituent particles. Okay. If you'll have any crystal, that means the atoms are arranged in a particular system. So now we are going to discuss about that packing in two-dimensional. Okay. So first it is the square close packing. In the square close packing, what happens, if we'll arrange some atoms in one array, we have to arrange the second array. The second atom is just below the first atom. You see, if we'll put the line, all these atoms are arranged in a straight line. Okay. Now, if we'll do this kind of packing, and the type we can say that that is A type. That means one array putting another array. First row, second row, all these rows are similar. So this type of packing we'll call it as a square close packing. And if we'll consider how many atoms are there which is touching one particular atom, that is 4. So this atom is touched by 4 atoms. So that means the coordination number here, that is 4. Okay. And it is AAA type. Next one is hexagonal close packing. Now we are talking about 2D, okay, two-dimensional. In the hexagonal close packing, first row is there. When we arrange the second row we have to put the first atom between these two atoms. Okay, so here is the atom. Again, between these two atoms there is another atom. Between these two atoms there is another atom. Okay, so this type of packing is known as hexagonal close packing. And we can say that this is BABA. Why? Because first row and second row, those rows are different. What is the coordination number here? The coordination number is 6. How can you know? See, look at this atom. This atom is touching how many atoms? So that is 6 atoms. So coordination number is 6. Now next type of packing is three-dimensional close packing. In the three-dimensional close packing, what we are doing in this type, all are AAA type. That means we have to construct one three-dimensional packing from the two-dimensional packing. So if you look at this diagram, this is one axis, this is another axis. So all these atoms are similar, right? And if you consider the third axis, that is this axis. So this axis is, this atom is just above the first atom. And third atom is just above the second atom. So this type of close packing is give us the primitive cubic unit. Okay, so this you can see this picture. This type of AAA type of close packing will give us the primitive unit cell. So this is a picture of 3D close packing. Now what is the coordination number? The coordination number here it is 8. Now let us talk about close packing, 3D close packing from 2D square close packing. Okay, so 2D hexagonal close packed layer A, place the similar layer above it such that the spare of the second layer placed in the depression of the first layer. See, understand the meaning in this type of packing. So first layer is done, right? This is the first layer and this is the second layer, and second layer is above the first layer. Here we are going to put the second layer in the depression of the first layer. You see, if you'll see this connection below this atom. So 1, 2 and 3. Okay, so the darker part of this red circle, that is above the depression of these 3 atoms. Okay, so if you'll consider this is one layer, layer A, this is a different layer. This is not the same layer as the layer 1. Okay, and so in this type of layer there will generate 2 types of voids. So what are these voids? Voids are nothing but the empty space. So in the solid there are so many empty space are there. So empty space are nothing but your voids. Okay, so here it is generated two types of voids. So one is the tetrahedral void, another is the octahedral void. So how can you understand which one is the tetrahedral and which one is the octahedral? So in the tetrahedral, tetra means 4. Okay, so when you consider this shape as atom, this atom, a darker atom, and this is another atom, and this is another atom. Okay, so in this 3 atom there is another atom which is just above the 3 atom in the depression of these 3 atoms. Okay, so if you can see that in these 3 atoms and above there is another atom, so there is a void created. So that void is known as, T stands for your tetrahedral. Okay, tetrahedral void is created by 4 atoms. Now coming to the octahedral void. So how a octahedral void is formed? Look at this picture. A darker circle and a lighter circle is there. Okay, so in the darker circle, if you see that 1 atom, 2 atom and 3 atom. Okay, in between these 3 atoms there is another 3 atoms is placed like this. So this is 1 atom, this is another atom, and this is another atom. So a octahedral void is created between 6 atoms, right? Can you see these pictures? Okay, so I think this is little bit clear to you. Then the next in detail, what are these tetrahedral and octahedral voids? Next we'll discuss about the tetrahedral voids. So tetrahedral voids, when a pair of second layer is above the void of the first layer, tetrahedral void is formed. So you understand this picture, or you see this picture. So in the lower part there is 3 atoms, and in the above there is 1 atom. So tetra means 4. So a void is created. So this void is called tetrahedral voids. So here you can see that these 3 atoms are there. The second layer is depression of these 3 atoms. So this is a tetrahedral void created. Tetrahedron shaped like this. Next is the octahedral void. The triangular void of the second layer is above the singular void of the first layer. So you can see this picture here. Below there is 3 layers. Okay, this is 1 atom, this is another atom, this is another atom, and the second layer is in between these 3 atoms. So this is second layer, this is second layer, and this is second layer. Okay, so in this type of arrangement, what we get a octahedral void. So you see this picture, this is layer A, this is layer B. Okay, so this is a created one octahedral void. So this octahedron shape is like this. And remember one thing, if the total number of sphere in a crystal is n, then octahedral void is n. Okay, that means the number of sphere, if it is n can be any integer. Okay, then the octahedral void is n, and the tetrahedral void is 2n. Okay, so you remember this concept. Thank you for watching this video. To get more video like this, subscribe to EDUKEM channel, and to connect with me with my social media account, my Instagram and Twitter handle is this.